Hey there everyone, it's Alejandro, and welcome back for day 86 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode medium grasp problem, and without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 210, course schedule 2. Okay, so continuation to course schedule 1. Let's see what this is all about. There are a total of num courses you have to take, labeled from 0 to num courses minus 1. You're given an array of prerequisites where prerequisites of I is equal to AI. BI indicates that you must take course BI first if you want to take course AI. For example, the pair 0, 1 indicates that you have to take course 0 to take course 1. Okay, same thing as before for now. Return the ordering of courses you should take to finish all courses. Oh, okay. If there are many valid answers, return any of them. If it is impossible to finish all courses, return an empty array. Okay, well, this is going to be very simple then, because it's just going to be what we did for course schedule 1. But instead of doing a count, return the actual topological sort. Okay, because I mean, the idea of this problem is essentially like, course schedule 1 is return true if there is an ordering that you can take, return false otherwise. And the way that we did that is topologically sort the elements and so on and like figure out, oh, is there an ordering? And if so, return true or false, right? But here it's just like, okay, instead of returning true or false, just let's return the topological order that we find, right? And obviously, like, there might be different orders, right? If you start off with two nodes with a 0 in degree, kind of like how I was saying with yesterday, like, between CSEA 67 and CSEA 08, you can take, whichever one first, and it doesn't really matter, right? As long as, like, you take a good ordering. We can just get straight into the code. So we have to do a topological sort again, so hopefully I can remember. So the very first thing that we should do, same thing as course schedule 1, but this time return the actual topological sort ordering instead of returning /fall. Complete or not. So here we can do an adjacency list is equal to course 0 for course in range num courses, and this should actually be an empty list, not a 0, because yeah, it's from 0 to num courses minus 1. And then we can just do, just like yesterday, we'll do an in degree dictionary, and this will be course maps to 0 for course in range num courses. Then we'll say for A, comma B in prerequisites, it must be that you take BI first, right? So BI points to AI. So BI points to AI. AI should be in B's list of neighbors. So adjacency list of B dot append A. And then in degree of A plus or equal to 1 because A has, whatchamacallit? Yeah, A is pointed to by B, so its in degree is now 1 larger, right? So now we have the in degree and we have the adjacency list. So here we'll just do topo order is equal to course says if in degree of course equals 0, right? For now, let's just print f string. I will call this topo order or topo sort or whatever. Then for now, return an empty array, right? Right, and then at the very end, it's like return topo order if length of topo order is equal to num courses, else an empty array, right? So that's essentially topo order will be incomplete if there was a cycle in the graph, which the case if and only if it is impossible to finish all courses as per the course schedule 1 problem. There we go. So yeah, so now topo order. At the very beginning, it's like, okay, you need to take course 0 before you take course 1, so it's the only one with 0 in degrees and so on. So this is good, this is good, this is good. Then topo order, what should we do? Here we'll say Q is equal to a collections dot deck of tuple order. Length of Q is greater than 0. Here we'll say course equals Q dot pop left. We won't actually add that to the tuple order and so on. We could, if anything, we could have this as empty, and then it's like, actually, when we pop from the queue is whenever we add something, right? So, but yeah, I'd rather just add the neighbors as we go, right? Then we'll do, for neighbor in adjacency list of course, then we'll say in degree of neighbor minus or equal to 1, if in degree of neighbor is equal to 0, then Q dot append that neighbor, as well as topological order dot append that neighbor, right? And this should be enough. Yep, so that works completely fine. So for now, let's just submit this. And there we go, bada bing, bada boom, 6ms solution, very nice and efficient, and so on. So yeah, okay, obviously, okay, this problem is very, very simple just because we did course schedule 1 in the previous video, which uses the exact same idea of like, doing a topological sort. And so it's like now instead of like, returning true or false whether or not there was a cycle in the graph, it's just like, okay, we know that there was a cycle in the graph if only if it's not the case, like, the length, the number of elements in the topological order is less than num courses, right? So in this case, instead of like, returning true or false, just be like, okay, return topological order. Instead of returning true, return the topological order. And instead of returning false, return an empty array, right? It's like literally the same algorithm, just change that minute little detail, right? So, okay, it's simple in that way. If anything, okay, are we able to leverage, like, the fact that things are from 0 to num courses minus 1? It'd be nice to get like a 0ms solution. Can we do things a bit more efficiently? If I use default dict, it ended up being slower yesterday. Yeah, this is faster. Instead of like, appending elements in here and so on, it's just like, okay, there you go. Can only be better. We could, so adjacency list, my keys are the nodes. And the nodes are from 0 to num courses minus 1. So they're just, if anything, I could make this an array, right? Instead of having key 0, key 1, key 2, and so on, I can make this like an array. And it's like, okay, index 0 would be course 0. So it'll be an empty array for I in range num courses, right? And that way when I do, yeah, of something like this, it's a node, it'll be the valid index. Okay, so we can definitely do that. So if anything, I'll comment this out. I'll put this here and comment this out. In degree, we can probably do the same thing, yeah. So instead of looking at a key A, we'll look at it as an index. So 0, here we can just do 0 times actually for this it's like, since it's by reference we shouldn't do times, but this is by value, so we can probably do times, right? So here we'll do length of or num courses. Does something like this work? Okay, nice. Nice. Okay, this is probably as efficient as I'm gonna get, right? So let's submit this. Okay, 4ms beats 52.77%. Okay, maybe if I submit it a couple times, I'll get around the standard deviation. But you know what? The point is that like we're right here with everybody else, so we have a nice and efficient solution. There we go. Bada bing, bada boom. That is exactly what we like to see. If anything, like maybe I could do like subtract and check at the same time. Right, where it's like, right, where it's like minus or equal. But honestly, at this point, it's just tiny O of one stuff and so on. doesn't really matter, and so on. It's like, okay, we know that we're in the pack, so it's a good solution. So there we go. Bada bing, bada boom. So as always, in all my videos, I do a quick recap if I was able to solve the problem. So for this one, it is exactly like course schedule 1. The only difference is that it's the same exact code. It's just that instead of returning true if there was no cycle in the graph, we return the topological ordering, and instead of returning false, we return an empty array for denoting that there is no ordering, right? So it's the very same concept as yesterday. So if you didn't watch the previous video, or not yesterday, but 2 days ago, or 3 days ago, and so the previous video. Essentially, what we do is a topological ordering of the graph, right? And one convenient side effect of a topological ordering, at least using, I think it's Kahn's algorithm, is that a nice side effect when you do the in-degrees method and so on is that if you end up yielding a topological ordering of the elements, and the length of this list is less than the actual number of nodes in the original graph, this is the case because there was a cycle in the graph, right? Any edge that isn't pointed to it starts off with an in-degree of 0, so it'll be captured at the very beginning. And then it's every other edge that you didn't add, it had some dependencies and so on. So if you end up doing a topological sort via this in-degrees method, Kahn's algorithm, and you don't get a full complete list, including all the nodes in a particular order, then it means there was a cycle in the graph, and that's why you cannot complete the list, right? So essentially, the solution is literally that. I just built an adjacency list for all the nodes. It's just, instead of a dictionary, I ended up using a list just to make things a bit more efficient. But you can use a dictionary like I have up here. For every course, map it to an empty set of neighbors, right? And for every course, its in-degree is initially 0. It's okay, for every single edge inside of prerequisites, and it's okay, B points to A, so add A into B's neighbors, and augment the in-degree of A by 1, because now we have one more edge that points to A. And then it's okay, for topological order, essentially it's initially start off with all the courses that have an in-degree of 0, kind of like in yesterday's explanation. It's we had the courses A08 and A67. You need to take A08 before you can take A48, and then you need A67 and then A48 before you can take CSC B36, right? And so it's okay, in this case, it's the 0 in-degree courses would be A08 and A67, right? So it's those are kind of the two that you can start with. Because they have no dependencies. And so then it's okay, we're gonna keep popping stuff from this queue. And so it's okay, at the very beginning, we're just we're gonna keep popping courses, which we essentially denote as taking them. Instead of adding to topological order in here and initializing it as an empty array, I figured I'd just include all the original 0 in-degree elements, and then whenever I consider a neighbor, adding that to the topological ordering as well. It's just a design choice, there you go. But the point is every single time that I pop a course, I essentially take that course, and then I'm okay, for every single other course that needed this course as a dependency, I can loosen that constraint, right? So for every neighbor of that course, I can say, hey, that neighbor now no longer needs this course as a dependency because I've already taken it, right? This course I have now taken, so this neighbor, right, whatever's in-degree it is, I'm going to minus or equal to 1, because it must have meant that part of one of its in-degrees values was from this course, so we can subtract that away, right? And at any point, if a neighbor's in-degree becomes 0, then that means okay, we essentially took enough courses that matches all of this course's prerequisites, right? We took all the prerequisites of a course. If a course is in-degree and it becomes 0, so in that case, it's oh, we can take this course. So what do? We add it into our queue, and we add it into our topological order, right? So here, if anything, it's if this is a bit confusing, you could do something like res is equal to an empty array, and here instead of this, it's just okay, res dot append or here tuple order. You could make there you go, an empty array, and then here's every single time you take a course, it's okay, that's part of the order of how I take a course, right? So maybe this is a bit less confusing, and obviously if I run this, we'll see that it still works, right? But the point is that okay, if this makes you less paranoid, where it's okay, we start off with all the courses that we can initially take, and then every single time we pop something from the queue, then we essentially say, okay, add it to the topological ordering, because we just took a course right now, so it's that is the next course that we took in our topological ordering, right? The logic ends up being the exact same at the end of the day, but maybe thinking of it in this way is a bit more intuitive, right? Start off with the courses that you can take from the very start, add them into the queue, you have not yet taken them, and then every single time you pop something from the queue, you've essentially taken that course, right? So you add that to your topological ordering because, like, you essentially have an ordering in which you take the courses and so on. So every time you take a course, add it to your list of completed courses, right? And keep the order, right? And then it's like, okay, once I've taken a course, every single course that has this as a prerequisite no longer needs that prerequisite. So I set its in degree, I dock it by 1, and then it's like, oh, if its in degree now becomes 0, then that means that's like I've taken all the prerequisites for a neighboring course, and so I add that to my queue, right? And a node will have an in degree of 0 only once, right? And then it's like, every single time I keep subtracting once and so on, so I don't have to worry about having a visited set and so on. I can just always check for this condition, and there you go, right? So every time, like, a course no longer has any dependencies for me to take it, then it's like I can append it to my queue to essentially denote in the future that, hey, I can grab this from my queue and take this course whenever I want to, and then that's like eventually I'll pop it because I keep going while the length of the queue is greater than 0, and whenever I pop it, I'll immediately add it to my topological ordering array here, right? I just happen not to do it that way. I just, like, what I did instead is I just like, initialize, like, inside of topological order, like, all those courses at the very beginning. Yeah, you know what? Honestly, it might make more sense to do it maybe just since, in my opinion, it actually is more intuitive to think about it this way, we can just leave it like this, right? So every single time, take a course. Remove course needed. Since now it's already been taken. There you go. And that way it's like, we essentially keep track of the ordering in which we take the courses. We initially start off with C for seeing if. There we go. That way it's like, it's just one nice line. Sorry about that. And then, yeah, so maybe, you know what, I'll keep it this way just because it's probably a more intuitive way to think about it, right? So it's like we have an ordering in which we're going to take the courses, right? We start off by adding into a queue all the courses that we can initially take at the very beginning, i.e. courses that have no dependency, i.e. they have an in degree of 0. And it's like we're going to keep going until the length of the queue is greater than 0. And every single time we're going to pop something from the queue, which essentially denotes taking a course. So we take a course by adding it to our topological ordering in which we've taken the courses, right? So like, very first course that we take and so on, we'll put inside of topological order. It'll obviously be the leftmost index value and so on. And then when we append stuff to the right of the array, we don't change the order, right? And so that way it's like, whenever I take a course, every single course that needs this course as a prerequisite, we're going to loosen that constraint because it is no longer needed as a prerequisite. That's why we subtract this in degree by 1. And then now, of course, if it's 0, that means there's no more any dependencies that we need to take that course. So we add that neighboring course into our queue for us to pop later on and add into our topological sort later on, right? And then at the very, very end, we check, okay, is the number of elements inside of my topological order equal to num courses, right? So essentially it's like, the topological ordering will give you an ordering of all the courses that you can take, right? Without like, an infinite cycle, right? And so if it's less than num courses, it's because there was an infinite cycle, right? And so an infinite loop, right? There was a cycle inside of the graph. Right, and so, and that's an if and only if statement, right? The length of topological order will be less than num courses if and only if there is a cycle in the graph, right? So it's like essentially return the ordering if there was no cycle in the graph and you can actually take other courses, and this is the ordering, one possible ordering of taking all the courses. Otherwise, return an empty list, right? And so that is return an empty list, denoting that, hey, there was a cycle in the graph, therefore there cannot be any topological ordering to take all the courses and meet all the prerequisites criteria every single time. So we just return an empty empty array, right? So it's very, very similar to the previous NeetCode 150 problem in that regard, like course schedule 1, right? And here we can submit this again. It might be a little bit slower than 4MS just because we do things this way. We'll have to see. So yeah, 6MS and so on, but it's relatively efficient. And honestly, I don't mind keeping it that way because this makes, like, you know, the code maybe a little bit more readable and understandable for the viewer. So I'll keep it as is, right? Even though it's just like tiny, like, you know, it's O of 1 stuff at the end of the day, so it doesn't really matter. And, you know, clean code, it does matter, right? So I might as well keep it in a way that's like, okay, this is easy to understand. Every single time I pop something from the queue, I essentially take that course, right? And then it's like, okay, every course that needs a prerequisite no longer needs it, and so on. So that's why I subtract the degrees, blah 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 blah, yada yada yada, right? So hopefully that solution made sense. And yeah, so at the end of the day, it's literally just topologically sort the elements using Kahn's algorithm. And, like, you know, if the length is less than num courses, there must be a cycle in the graph, so you cannot take all the courses in a valid way, so you return an empty array. Otherwise, return the topological ordering that you found of all the nodes and the ordering of which to take them to never break, like, you know, taking a course without having a prerequisite. And there you go, bada bing, bada boom. That is how I solved this problem. So as always, let's make sure that we come in here and check off the fact that we did this problem. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So until then, ciao ciao, my friend. Bye bye.